get once again the opportunity to thank everybody who made this possible, George, especially for all the local arrangements, and Julia and the folks at IU. And what do you say we all come back next year for the second annual
60th birthday?
60th birthday, sure. Okay, we're going to end with 3 great talks. The first one is Jonathan Sobel, implementing categorical semantics.
Right. So because everyone keeps asking, where am I now? I'm at SAS Institute along with John Rossi, and it's the place you may have heard of for doing stats software. People in social sciences and financial industries and things use it. It's the largest private software company in the world. It's over 10,000 employees. It's based in North Carolina, in the Research Triangle area. And we make software of all sorts for crunching on data. This is not directly related to that, although some of the results from this may go into something there. This is related to the work I'm doing with Dan as part of my dissertation here at IU. All right, so the title here, Implementing Categorical Semantics, all 3 words of this are important because we care about implementing, because that's the kind of people we are. This is about meaning of programs, this is semantics, and the categorical part is what gives us a little problem because we have an enormous range of backgrounds here in the room, from people like Mitch, who at the very first 1985 conference on category theory and computer science was already credited as being one of the people who brought category theory into computer science between 10 and 15 years earlier. I don't know if you know that, you're cited as one of the people who brought category theory to computer science. And we have other people in the room who might not know much category theory. So, that means that I'm going to, oh, we're not syncing properly. Come on, what is this? The auto sync thing.
What software is that?
Yeah, what kind of lousy software is this? This thing had synced itself up nicely. There we go. There we go. All right, so to remedy this problem, I'm going to make sure that we all know category theory in 2.5 minutes. All right? So the first thing I want you to think about, let me back up here for a second, is not category theory. I want you to think about Turing machines. Now, Turing machines can serve as a foundation for all of computing, right? No. Okay, let's set aside that quantum stuff for a second. Turing machines can serve as a foundation for all of computing, right? And on the other hand, we have lambda calculus, likewise, right? And they can be proved to be completely equivalent. Anything one can do, the other can do, right? But they feel so different. Turing machines, your instructions are these little, mark little bits on tape very imperatively and move a little square over here and a square over there. And your whole program is just this giant state transition rule thing with no structure to it. Whereas lambda calculus actually has the notion of functions built into it. It has as its primitive operation something that seems much higher level, which is this beta reduction rule, which includes the whole renaming thing of alphas to go into it. So it's less primitive, but it's just as foundational, right? With a big different feel to it. Well, set theory is kind of like Turing machines. It's this very basic thing. Everything's encoded in element of. There's not really much structure and relationships primitively. You encode that through pounding sets inside each other and building stuff up. And category theory is a little more like lambda calculus, in that it takes some things like structure and relationships as primitive elements of the theory. Both of them can serve as foundations of mathematics and be proven to be equivalent, just like Turing machines and lambda calculus. So if one of the primitive things in it is relationships, how do you express structure and relationships mathematically? There are several ways. One of the crucial ones is graphs, right? You got a bunch of nodes and a bunch of edges, or as category theorists call it, objects and arrows. The objects often have some kind of semantic weight outside the system, but in the graph, the really important thing is the relationships expressed through the arrows, right? There's lots of graphs in the world. Understatement, right? But category theory says that some graphs are more interesting than others. So in particular, useful graphs have reflexive relationships in them that says every object has at least one self loop that just says, I'm me, and that's it. And those are the identity loops. Useful graphs express transitive relationships, which says if I can hop from A to B to C to D through a sequence of other arrows, then there better be one that expresses the composition of all of them and is equivalent exactly in every way to that pieces of paths. And furthermore, we'd like to think of it as the path, H composed with G composed with F, and not worry about order. And so useful graphs express associative relationships. If you have a graph that's like this, you get to label it category with the big category stamp, and now you know what a category is. Now, all the rest of category theory, about half of it, plus or minus epsilon, is concerned with finding interesting classes of categories, like you have some special object, like say the thing called terminal objects, or maybe there's this special object in my graph. It's really unusual. There's exactly one arrow to it from every other object in my entire graph, including itself. Its identity arrow is its only self loop. That's kind of an interesting kind of graph, right? It's an interesting class of categories, categories with terminal objects. So things like that, where it's some property that's universal with respect to the rest of the category of some arrow or object. Or the other half, plus or minus epsilon, is relationships between categories, like how can I take this category and embed it in that one, preserving the relationships, maybe folding some away but not breaking any. Or if I have one category and another category and I can embed it this way or embed it that way, what's the delta between the embeddings? That's a natural transformation. That kind of stuff. There, now you know category theory. Well, at least enough that you might recognize it if you bumped into it at a birthday party. Now we're going to talk about categorical semantics. What is a categorical semantics and what kind of program are you writing when you build one? Categorical semantics, let's start with a little simple language, a familiar looking language, lambda calculus, but I've written in scheme syntax, so single argument functions and application. What a denotational semantics does, what any semantics does, well, there's operational semantics, which tells you what the states of your program are as you go along, and there's the denotational mathematical kinds of semantics, where you take programs and you say what they look like in some mathematical realm, and then you end up talking about things like, well, programs that are equivalent at the term level ought to be equivalent in the mathematical level, and you get to how equivalent are they between the two and full abstraction and all that kind of stuff. So the usual denotational semantics we're used to seeing are things where you have some kind of meaning function that says for each kind of term, there's a meaning for it, and in the context of an environment, I say some mathematical denotation. And the really common one we're familiar with for that mathematical denotation chooses lambda terms. And so the meaning of variables is look them up in their environment. The meaning of lambda is some function that, when given a value, will figure out what the body is in an environment where the variable is bound to the value that came in, and application is just evaluate the operator and the operands and put them together. Now the cool thing about this is just about everyone in this room can see this and have a running implementation in like less than 60 seconds, right? You just type it in. That's cool. Here's the scheme program. And it just says the same thing, meaning of expression in the environment, go through, look up your variables in the environment, run the body of the lambdas in the extended environment, evaluate the operator operand. It's just the same code. I mean, to us that looks like an identity arrow, right?
It's also 5 lines.
3 lines. Don't you know how to count?
You can fit this on it. You can easily fit this. Even a 3x5 index card. All right, so now let's try to do the same thing with the categorical semantics. What do categorical semantics look like? So the important thing here is that a denotational semantics becomes an interpreter very easily for us. Well, categorical semantics is funny. First of all, you guys know the Church versus Curry style of semantics. Curry says that you have programs, and one of their properties is that they have types, and you can go and sort of type them later. And Church says, no, there are well-typed programs, and those are programs, and there's other stuff, which is some symbols you put together, and those aren't programs. Categorical semantics is pretty squarely on the Church side, which is it does not say anything about semantics of terms that are not well-typed, right? So we're already a little different in that we need to know our terms have these types. And so to do that, we have to have type rules that say, for instance, the variable x has the type, x of I has tau of I. If you have some typing context that says somewhere in there I found it, and it said it was that type. Or lambdas, lambda has this arrow type, sigma to tau, if in a typing context extended where I know that x is sigma, the body has type tau. And application, it's the usual check to make sure that your operator is an arrow type and your operand matches what it expects as input. Given that, now I can define a categorical semantics. And it just takes basically every rule of every line of one of these sort of things and gives it an arrow and a category to go with it. So variable reference turns into, this is a projection operator, pi, which says given a tuple of values, project out the ith one. Lambda turns into, given an arrow that goes from a tuple that includes the bound value to the output, curry that thing. so that I take everything but the bound value and get something that when I get the bound value, I'll be able to do the work. Kind of makes sense, right? So that capital lambda operator is curry. And application is if I have an arrow that tells me, computes the body for me, computes the operator, and I have an arrow that computes the operand, then I can put those together and apply an application arrow to them and get out the result. Right? Now, quick write an implementation for me.
Cam done 1984.
Okay. I don't know the citation you're referring to. Which one?
Categorical abstract machine.
Right. Right. So okay.
Does it fit on a 3x5?
Yeah.
So let's hold off on that. If I don't run out of time, I'll address that. Okay, and say what the inadequacies of the CAM are and how I'm extending beyond that, because of course I've looked a lot at it. But I'm going to bypass that for now. It doesn't feel as easy as what we're all used to, right? And I'd like to look at, why. So first question is, can we turn this into an implementation just as we did the lambda-based denotational semantics? The answer is definitely yes. Is it clear what code to write? Is it less clear? And I think it is a little less obvious to most people in here if they don't know that paper. And it's probably still less obvious than it is to do EOPL kind of thing. In the denotational semantics, the denotations were these lambda terms that already kind of looked like scheme. We knew how to type that in, right? Our input in the categorical semantics, and I should put a little disclaimer that categorical semantics is a kind of denotational semantics, but I'm making an artificial distinction here to say this specific kind versus that other thing we're used to. We're less familiar with using proof trees as an input, right? We're really used to taking just program trees, but what do proof trees look like as inputs? And we also have just gotten used to the kind of pattern matching of looking at one and reading the other, right? So that pattern is important to us, and it's an important thing we've learned from people like Dan and Chris and Mitch. And as our output, we get these arrows, and it's not quite as obvious what to do with those as just I have lambda terms. Those are kind of like scheme code. I can just run them. So once we build this interpreter for this, I'm assuming we get over all these problems, is it going to look really different from our EOPL interpreters? Let's look at it a little bit. In fact, let's look at one particular rule in there. Let's look at variable reference. In the old regular denotational semantics, it says, look in the environment and get the value of the variable. Right? In the categorical rule, it says, look in the type context to get the lexical address of the variable, effectively, in order to generate the arrow, which will be the right projection arrow. Okay? So, denotational semantics, input is program with environment, output is value. Categorical semantics, input is program with type proof, output is instructions for computing the value later. That's a funny interpreter that hands me instructions for getting my values later. I don't usually call those interpreters. So I would argue that a categorical semantics doesn't give you an interpreter, it gives you a compiler.
Well, that's true for denotational semantics too. I mean, that's what a denotational semantics really is. An operational semantics is an interpreter. We just went along with you until now.
But so do so many other people. Come on, stay with me. No, so there's, so I am talking partly here, no, to be serious. I mean, so when we looked at those M terms, it's curried, right? And so the thing I get back is really lambda row of x, right? Which is a slightly different thing. So I'm also talking partly about the pedagogical value of this and how we tend to read these, and that we haven't been given the pattern for reading these in the same way. And it's also still true that that little function says, the little lambda row of x, to when I get a row, look it up and get out the value, right? With a sort of name-based lookup. There's nothing in the base semantics that talks about doing lexical addresses. And I would say that if you look at the difference between an interpreter and compiler, you can actually, as a little crucible of the difference, look at variable reference and say, am I getting values out of variables, or am I just figuring out how later to find the value in a stack frame, or however you want to represent your values that will be available. And there is crossover, and it's close, but there is a difference. Okay? Okay, so let's suppose that I then let's just say what to do with those arrows, right? And part of what I do in my dissertation is I say, and part of what's different from the CAM, is rather than taking those arrows as instructions for a machine, which is what the categorical abstract machine did, is take those arrows as an intermediate language, which you then use more traditional compiler techniques to grind down to machine code. All right, and there is some important difference going on there. And part of the argument is that those make a useful intermediate language for actually doing real life. I'm not just talking about in a theoretical domain here, but for actually doing useful optimizations and things, because you can use the equivalences there to do the kinds of things you want to do in a compiler. And it gives you a really nice front half, back half breakdown where you can say, here's my language semantics, and here's the part that gets me down to the category theory, and I can implement this arrow compiler as the back half and share it with people, and they can implement their categorical semantics also. Okay, so let's suppose we do all that. There's this other interesting piece of this, which is where do I find a categorical semantics to do this with? I'm all set to go now, ready, let's go implement. Where do I find one of these categorical semantics things? Well, you'll find them lying around at conferences, but they're not quite ready to implement. So where do I find them? I'm going to turn to a different important person besides Dan temporarily, and that's Dana Scott. But from a different birthday celebration. It's a really important paper. You guys been looking at this one too lately? Okay, it's a beautiful paper. Beautiful paper. Dana Scott can seriously write. And at Curry's 80th birthday party, I'll give you several quotes from him. He said we ought to think about not just where our theories did come from, but where they should have come from. Kind of rewrite history a little bit and see how things really fit together in hindsight, regardless of whether that matches history or not. And another thing he said is that when you're looking for a foundation of something like lambda calculus is about functions. It sort of is a theory of functions. And so if you're going to base that on something in math, it's going to be an even purer theory of functions than lambda calculus itself. And he says that the ultimate in the pure theory of functions is category theory. Right? And here's the really important one. He presented this paper at Curry's birthday party right after a paper by Lambeck entitled From Lambda Calculus to Cartesian Closed Categories, where Lambeck shows that any lambda calculus is a Cartesian closed category. And if you don't know what a Cartesian closed category is, don't worry about it yet. It's just a proper noun. I'll define it in a minute. But it's one of those interesting classes of categories, right? I said, some categories have special properties that make them interesting. That's one class of them. He said he could have called his paper Cartesian closed categories to lambda calculus, because he's trying to figure out where lambda calculus should have come from, not where it did come from. And he says that we should look at Cartesian closed categories as the starting place, and then look at lambda calculus as coming out of that, right? Now, he was really thinking of this as a philosophical exercise, but I want to do sort of Dana Scott on steroids and think about, let's really take this to heart as a way of arriving at languages. Right, you're picking of Dana Scott pumped up, like Arnold Schwarzenegger. I want to actually take this as a guideline for where do we find our languages, at least for the really core of our languages, and say that we should start with the math. Start with your mathematical constructs that make sense and derive your languages from them, which is not the thing we usually do. In fact, in the categorical semantics realm, what people usually do is they take it as descriptive. They have some interesting thing they thought of, and they come up with a way to describe that categorically. But I'm talking about being prescriptive and not descriptive. So we start with our math, and we use that to prescribe what our language is. That leads me to my first law, which is trust the math. The math is right. If the math says it, it's true. And I'll reference a physics hero of mine here.
Paul Dirac.
What? Paul Dirac, absolutely. So you guys are already ahead of me there. I don't know if you know the story. Paul Dirac was a physicist who did the work that put together Einstein's stuff with quantum theory. Really great guy. Lots of great stories about him. But the one that's important to us right now is that he saw that in this math, and I think it was actually in the E equals mc squared. Doesn't it come out as e squared m squared c to the fourth at first in the derivation? So there's an m squared in there. Well, okay, we can just square root that and get the whole thing, right? What's the square root of m squared? Plus or minus m, right? And so everyone said, well, okay, but clearly negative mass is a stupid thing. It means plus m. Dirac was the one with the courage to say, no, the math says m squared. Therefore, one of the answers is minus m. And it was about 15 or 20 years later when someone finally demonstrated that antimatter existed. But he believed it because the math said it, and I think we should do the same thing in programming languages. And so I want to start with mathematical principles and then get our languages out of it. Now, what's cool with category theory, in fact, is that these interesting classes of categories kind of have a hierarchy. You have just categories. This is all possible categories. And you could say, what kind of languages do I get out of that? Well, it's pretty boring languages. It's sort of sequenced operations. That's about all you can say. Well, what if I say categories with terminal objects? Am I really at 5 minutes? Wow. Okay. Categories with terminal objects, you can get not much more. Some of those operations can take no input. How about with products? That's Cartesian categories. Oh, now I can get a little language of commands that are multiple argument and compose them up in interesting ways. What about with exponential objects? That's like function spaces. Well, that's really cool. Now I've arrived at this thing which was really interesting mathematically in its own right because it can represent its own arrows, and which is called a Cartesian closed category, and the language you very naturally get out of it Just kind of squeeze a little bit, and out pops simply typed lambda calculus. Right? Let's keep going. How about sums? It's not clear which order these ought to go in, but this gives you distributive categories where I finally get to do variant case. How about something else? A thing called subobject classifiers. And there is a sort of an ordering to these as you build up. Or what you think of as characteristic arrows, which is like in sets, if I have one set and a subset of the other, I can have a function that tells me which elements of the target set are in the range of this function. If you do this, you have a thing called a topos. It's another very interesting mathematical thing in its own right. It is capable of representing first order or really higher order logic. What kind of language do you get out of that? Well, there's like whole books on what kind of language do you get out of that, but it's presented in a way that's totally non-implementable. Right? I would say that no one has ever done an implementable categorical semantics for anything beyond right here. Let's keep going though. Let's add data types, one of the things that Mitch actually was being credited with in that early paper. So I can have lists and trees and streams because I really like those. There actually is a correspondence for that in the category theory such that you get them in your language. But this is one of those places where you get interesting things. If you really trust the math, you get different operators out in your data types than what we're used to for programming. Right? And I don't have time to say what some of those are, but I get these things out and I go, I've never seen that in a language. I don't know what to do with that language form. I have no idea what the software engineering impacts are. But the math says it's there, so I'm going to be like Dirac. That must be one of the fundamentals of my language. Right? It must be those basic loop things. Right? This must be the real base of what loops are. And finally, this level of language, this level of language is still terminating. You know that? Even with streams in it.
No.
All my programs terminate. Yes. Never mind that paper that said that if I have both katas and annas, I get y. It was wrong.
Oh, good.
This still terminates, which means I can write programs over streams, and they will terminate because I can't write the program length of the stream of natural numbers. Until I have a particular kind of monad, when I can suddenly write length of stream of natural numbers, I can pretend that stream is a list. Right? At that point, I've got an interesting language. I can do cool stuff. Okay, so this is the way I actually derive languages from the math, and then I think that serves as a foundation for more stuff. Okay, now how much over am I? Can I say a couple of Dan things? All right, so finally I have to say what all this has to do with Dan, which is the comb problem. The problem that ate my life. About 10 years ago, Dan presented to me the comb problem. The C was for the Klinger compiler, or by which he meant broader stuff. And he actually called it this. He called it the comb problem. The C was for the idea that you take a language and you somehow get a compiler out of it sort of for free just by grinding away based on the structure and syntax of the language. And semantics of the language, rather, which is a thing that Will Klinger did. And object-oriented programming was the O part. Objects are kind of cool and interesting. You got subtyping, you got ad hoc polymorphism. The M part was monads, which we were just getting interested in around here. And particularly the sort of composition problem and the monad reflection part. And the B was, of course, book, as in essentials of programming languages. Really capturing the whole idea of you ought to understand languages by implementing them. It ought to be easy for anyone to implement languages. You know, anybody ought to implement a programming language. And you ought to be able to fit it on a 3x5 card. He said, these things have a deep relationship somehow. Think about it and figure it out. Yes. Oh, I mean not parametric polymorphism. I mean the kind of polymorphism you get in object-oriented programming as opposed to the kind of polymorphism you get with identity function. So I won't give you the full story of the narcissistic experience of my life for the past 10 years going through this, but I started with the monad part and the reflection part, but I immediately ran a sort of Brian Smith's 3-Lisp problem. In order to do 3 Lisp, I don't know if you know this, he needed a sane Lisp underneath it, so we had to build 2 Lisp. Well, if I'm going to work with monads, I need a sane categorical-based language underneath it, so I need to go implement one. Well, surely someone's done that, and I started with the kind of cams. But it turns out, as you keep going backwards for interesting languages, I eventually, finally, about last year, realized no one had ever even written down a categorical semantics in enough detail for anyone to implement it. And there's a whole bunch of things that in doing it, I'm discovering that I believe are fundamental and interesting results. And it's just that no one has implemented them before, which gets us to the second law. Don't believe anything until you implement it yourself. Yeah. And if the other one goes to Scott, this one goes to Dan Friedman. And in fact, the 2 laws together are exactly the thing that Guy referred to in the Little Lisper. First think about it, then try it. And you have to do both. And so It's because some of these other people who think they've done things, and have done them mathematically, haven't ever tried to build them, that I've suffered all these years. So I'll give you one little example. I know I'm way over time, but I've got to throw out one tidbit because someone here who's like an undergraduate or a young graduate student will get stuck on it, and then they'll be miserable for the next 10 years. So one little example of this is, you heard Steve mention a thing, which a lot of people mention, which is that you can treat functors as the type constructors. Think of functors in a category as type constructors. Now, if you try and get serious about that, you actually have to hook all that into your language semantics, right? And if you want to do data types, you have to kind of do this. But you really have to come up with the semantics for those. And if you really try and make all that semantics fit in and not just kind of wave your hands at it, that's not what it's like to see. If he's working on very well-founded research that just didn't happen to implement stuff, then you discover that you have to come up with the entire semantics of your type level, and you rely very heavily on the fact that the meta level of category theory, the categories and functors, themselves form a Cartesian closed category. But wait, I know what to do with categories. I squeeze on them and I get out a compiler, right? So I can get a compiler out for my type level. And what do I do with that? Well, I have to use that type compiler to compile my types into something that I can run at compile time to work with my code. Now, it sounds really funny to have code that compiles and runs at compile time in order to compile the rest of the code. That sounds to me a lot like macros. And then I have to ask myself, is there something really deep here? Somehow we in the scheme community have survived without static type systems for a long time. Is there something about the relationship between types and macros that enables us to guarantee a kind of correctness in our programs through macros that's enabled us to go on this way? I don't have an answer to that, but it's the kind of thing I discover when I try and build these things. So with that open-ended problem, I'm done. Yes.
When he came here and gave a talk, I invited him up to see him, and then I started through when he third author
Okay.
to
Yeah.
talk about the camp.
This is one of the authors of the thing called the categorical abstract machine. Where let me say real quickly what that is. That is, take those arrows that come out of the categorical semantics and just treat them as machine instructions. And Domvi.
So the question is can your work be represented as a bunch of staging transformations all the way down?
I don't know. Honestly, I hoped to explore that kind of stuff, and it's taken all the time just to work out the details of the implementation. Yes.
So I think you didn't really finish the answer to the first question, which was, what does an implementation of a categorical semantics look
Oh,
like?
I forgot to bring my 3x5 card. What it looks like is just in there before your place where your interpreter / compiler thing would go, you're going to have a type checker phase that builds the type proof. And then you're going to have things that work over those type proof trees to, at that point it looks like a regular interpreter, but the thing you're getting out is some kind of representation of arrows. Right? And at that point you could decide to take those and immediately turn them into something you could run, scheme lambdas or something. Or to take those and grind them on down to actually native code.
I think I'm going to have to see the 3x5.
Okay.
Maybe we should follow the second.
Jonathan, if we're one of those people who tried to follow along as best we could, but we really need to sit down and read it very slowly, what's a good source? Is your thesis cover this, or
Yeah, but it's not published yet. So, there is not a good source to cover this stuff. So unfortunately, one of the pains I've experienced is that I've had to do some combination of computer science stuff and reading right up at last year's math journal to pull out pieces I need. And I don't feel like I should have to do that, but someone's got to slog through that stuff once. It seems like a dissertation is the right place to do it, to export it.
There's a very good description of the category theory in computer science. It's not Jim Pierce's book,
Right, yeah.
which is a bad description.
Yeah.
But it's Steve Easterbrook. He's a software engineer at Toronto, and he's got some very
Okay.
nice work on this.
Yeah, part of my dissertation also has a rather unusual description of what category theory is.